Not the wall, but yeah, okay, the component,
Yeah.
some
Mm,
component. Can you give us an idea of what are, like, let's take one property, because there is so many, right? Like toughness and resilience, I guess, and many other but let's take one of it, and then maybe you can walk us through before the treatment it was that, but then with the treatment it improved at that much, or I don't know, the cycles of life extended at that much, or so we have an idea of proportions of
improvement,
resistance
yeah,
or
change. Okay, so let me just first something in face. So in research and also in the literature, it can be find quite a contradictory results actually. When you use the same steel, some researchers see, wow, very positive results, so really improvement to everything. On the other hand, for the same steel, the other researchers see really negative results of after application of cryogenic treatment. And then we have also the third group of researchers who say, oh, sorry, we don't see any change. Why would we even apply for that?
good morning, good afternoon, or good evening, depending on when you are watching us, and thank you for being part of the material business community. My name is Monica Hernandez, and I have a really special guest today, Patricia. Thank you for coming this second time into the podcast.
Thanks for the invitation.
So today is really nice. We're going to talk about, I'm going to read it because it has a lot of terms that I'm not used to. So we're going to talk about cryogenics in the energy sector. So Patricia is a pioneer in the field of cryogenics with applications in the energy sector, currently in fusion. That sounds very interesting. She'll present her role in cryogenics and how she combines different fields and perspectives in one research, which can be applied not only in the energy sector but also in other sectors, such as medicine, music, oil and gas industry, mining, material science, etc. I was really looking forward to this because it's not very often that we have someone in the podcast that can relate so many points. And I was thinking about Alec Groisman. He wrote a book, and one of the chapters is how corrosion relates to all of the other things: economics, art, music. And as I heard this description, I was like, oh, this correlates so much. So thank you for being open to share. And the floor is yours. What is all that cryogenic thing?
Thank you, Monica, for the nice introduction. So thank you for having me back at your podcast. So what is cryogenics and how does this correlate with material science and the work that I'm doing currently? So cryogenics is a field. If you look into statistic, less than 1% of women that are present and doing the research, and even less are working in material science because most of them are working in physics. So let's say I'm 0.2% of women working that, and what I'm doing is cryogenic treatment. So cryogenic treatment is a way of treatment or processing the material when instead of warming up the material, we're actually exposing to sub-zero temperatures in order to change its microstructure and reduce final properties, such as mechanical properties, corrosion, wear resistance, etc. In our material science, we know actually three types of cryogenic treatments. The first one is so-called conventional cryogenic treatment, where the temperatures, I'm going to put in Celsius, are between minus 0 to minus 80 degrees Celsius. Then the second one is so-called shallow cryogenic treatment, where the temperatures are between minus 80 to minus 150 degrees Celsius. And third, last one, but in my opinion, the jewel of them all is so-called deep cryogenic treatment, and also is a treatment which I am applying on the selected materials. So here are the temperatures below minus 150 degrees Celsius, usually around minus 196 degrees or 77 kelvins, which is the temperature of a liquid nitrogen, which is also the most commonly used media for cryogenic applications. However, in DCT or deep cryogenic treatment or processing, we can also use liquid hydrogen, which is also now that's more into research because we're trying to transfer hydrogen, and that's why more research in this, how hydrogen can be transported and also then used for the energy is done. last but not least, we can also use the liquid argon and helium in some cases, which is around 4 kelvins, which is a minus 96 degrees, in which case we can actually say that yes, we are almost to absolute zero. So here we also can talk about millikelvins if we do this kind of research. So what I'm doing, so in my research, my past, current, future research, I'm doing for applications on cryogenic processing for the energy sector. So in my PhD, I did a lot for the tooling industry, where I tested different tooling steels, so for the cutting applications, also did for the different bearing steels, stainless steels, and also some non-ferrous alloys such as aluminum alloy, nickel, and titanium alloy. However, selected, of course, not all of them. However, in the current research, I am giving more time on the possible materials which can be used, are actually considered to be already used for the first wall for the future fusion reactors, such as Uro 97, with which I collaborate with my colleagues from KIT, so Karlsruhe Institute of Technology, which they provide the material. However, in order to understand how is cryogenic treatment changing its properties, so till now, for example, my past research, I did, of course, a lot of microstructure research, then mechanical properties, which shows we have a higher hardness of the application of cryogenic treatment. And also now, which I'm just confirming, we also have a higher corrosion resistance in extreme environments of our cryogenic treated samples. And my current research, which is with Marie Curie fellow, which I become with September on, I'm also testing alternative materials such as selected martensitic stainless steel in order to be applicable for the fusion applications if we change it with the help of cryogenic treatment. So this is, let's say, my current research and also my future. However, cryogenic treatment, let's say we go back, can be applied in different disciplines or fields from the music industry, because they say if you apply on the brass or string instruments, they can actually have a better sound after they went undergo cryogenic treatment. That can be used in the oil and gas industry for the pipes applications. They can be, of course, used in electronics and robotics for the specific components to apply it and to change the properties. And also in the medicine, for example, for the applications on the implants, such as hip and dental implants, which is also an interesting field, which I'm also trying a little bit dive into that. I did a little bit already in my PhD with titanium implants, but now with the colleagues from the Duisburg, and also we're trying with the neighbor Max Planck Institute to try dive more into more, and also for actual, so not just treated it, but to observe if it's more, let's say, more corrosion and wear resistance in the actual biological environment. With my colleagues from Fraunhofer Institute in Slovenia, we're also going to be some bio-inspired coatings to actually try to provide really biocompatible material with biocompatible coating in order to challenge the current coatings and implants for the usage in medicine. However, this is more going to be focused on the hip implants. But my main project, of course, is for the fusion.
Wow, that sounds incredible. And then, like you said, it touches many different areas of life that nobody would have thought about, like music, for example. Who would have think that a little bit of changing in properties will change the sound? But now that you think about it as a materials engineer, obviously the microstructure will determine how that vibrates and then how that sounds. So it is very interesting. So is it just to back up a little bit, the cryogenic is just changing the structure at the surface of the material, or how is that?
So actually, the cryogenic processing or treatment, it's a unique technique or process where at the same time we are treating surface and bulk of the material. That's why so many different changes and properties can be changed at the same time. That's why we say, okay, we have improving the corrosion wear resistance, but at the same time we have improved toughness, strength, hardness, etc. Also magnetism, of course, because we are changing microstructure.
So in your current research, you said you're working on applications of fusion. So how is that working? Like on what? And I know that there are some things that you cannot disclose because they are proprietary, but as much as you can with the information you can share, like, so our audience can imagine, where can those materials go exactly within the chain of production, let's say?
So, for example, in my past research with our Sample Humboldt Fellowship, I did research on the Uro 97, which is a material to be considered as the first wall of the new fusion reactors. And with the current project, I'm diving into alternatives, so challenging material, also materialistic stainless steel, which can be actually applied if we prove it to cryogenic treatment for some components and pipes, supplying systems, and so on. So actually supporting systems of the fusion reactors, not directly the wall.
Not the wall, but yeah, okay, the components, some components. Can you give us an idea of what are, like, let's take one property, because there is so many, right? Like toughness and, well, resilience, I guess, and many other but let's take one of it, and then maybe you can walk us through before the treatment it was that, but then with the treatment it improved at that much, or I don't know, the cycles of life extended at that much, or so we have an idea of proportions of resistance or
Okay, so let me just offer something in face. So in research and also in the literature, it can be find quite a contradictory results actually. When you use the same steel, some researchers see, wow, very positive results, so really improvement everything. On the other hand, for the same steel, the other researchers see really negative results of after application of cryogenic treatment. And then we have also the third group of researchers who say, oh, sorry, we don't see any change. Why would we even apply for that? So what is the reason? So let me just maybe some basics. So on cryogenic treatment, there are 4 factors that really, let's say, influence on its performance. First is cryogenic temperature, so the temperature to which we select that our materials is exposed. The second factor is the soaking period, so how long our material is exposed to selected the sub-zero temperature. Third is cooling and warming rate, so how fast we're cooling and warming up than our material when it was exposed to cryogenic treatment. And then last but not least is also the placement. So when during our heat treatment, the cryogenic treatment is applied. Let me give for ferrous alloys, let's say for the selected stainless steel that I'm using. So the selected temperature is minus 196 degrees Celsius, so 77 kelvins. The time when I'm using is 24 hours. However, I'm trying to minimize it to actually go from 24 hours to the maybe 8 or 10 to get the optimal results. This I'm also doing. The third step is I'm not trying to exceed 10 Celsius or 10 kelvins per second cooling or warming in order to avoid microcracking. This is also recommended for the steels. And then last but not least, application of microcryogenic processing is after hardening. So when austenization and quenching is done, it goes to the 1 cycle, which can be followed by 1 cycle of tempering, or in some cases, such as austenitic stainless steel, martensitic, we don't need any additional step of the tempering. So that's how it usually plays. However, in the last years, we also have applications called multicycling, where we actually change the temperatures of shallow and deep cryogenic treatment in order to manipulate the final microstructure. So in regards to that, depending which cryogenic treatment do we use, that's how we can actually phase the changes. So the changes of the cryogenic treatment are not only defined, of course, by temperatures, but we also observe the changes of the microstructure. With the lower temperature, the higher precipitation of the carbides we can observe, also nanoscopic ones, such as M23C6, which are usually enriched with the chromium or iron in steels. And then also with what we observed, that we have minimization of the presence of the tin austenite, which can be in the last even below 1 volumetric percent. So in one case, what I'm doing is around 0.1 volumetric percent only present. So in regards now to this, when we see now microstructure changes, how this correlates with the properties. In my research, for example, also with tooling systems, so what I observed is we can improve mechanical properties up to 30%. For example, hardness or micro-hardness was improved up to 20%. Then we have, for example, fatigue resistance, so which is correlated to our how long is going to live our material component, can be improved even up to 50% in some cases. Yeah, after our application of cryogenic treatment. And then, for example, when we talk about wear and corrosion resistance, we can actually observe up to 75% improvement. Again, depends on each material. So here is the trick. On cryogenic treatment is not only defined by these 2 factors that we discussed, but also from the steel type. So it is powdered, so powder metallurgy or wrought steel. Then what is the chemical composition of the steel? Then we have, of course, the selected austenization and tempering temperature can manipulate the successful of cryogenic treatment. And last but not least, is also phenomena which is already present in the microstructure, such as twinning or plasticity-induced transformations and so on, or artifacts. Let me just briefly say, so with the research of stainless steels, which is also my main research, what I observed is for the given martensitic stainless steel, which I'm researching, which is AC431, I can say. This is no NDAs here, but for Eurofer I cannot say. This is also published results, is that I observed so-called CART effect, which I give the name. So it's cryogenically induced artifact. So oscillation transformation. Why it's happening is actually the cryogenic treatment is suppressing this transformation, which is causing that we have changes in the end. And before, martensitic stainless steel, which was nothing special, is now considered to be as the third generation of high-strength steels. So you can see with manipulating the microstructure with cryogenic treatment, we can actually manipulate the properties, and also for application of its material can be actually not just for one application, but also for another one. So in regards to corrosion, for example, if you dive more into, also what I'm doing also more research into corrosion and surface analyzation in my current project, is also that we observed for specific tooling steel, which was H2, so it was high-speed steel, that actually when you have a corrosion in the cryogenic treated steel, which was exposed to liquid nitrogen, this is an important factor, is we have actually so-called ghost layer, which is enriched with the nitrogen. When we did the Raman, Raman XPS analyzation, what we observed is actually that we have a specific layering which is causing improvement in corrosion resistance. For example, in a cryogenic treatments, first we have called green rust, first or second type, which is enriched with nitrogen, on which magnetite is formed, and only on that all the other oxides are formed. And these two layers act as a really active passivation layer, which help improving corrosion resistance of cryogenic treated samples. What we just observed also with our colleagues here is that when we compare conventional, so a normal treatment, we have more presence of chromat for my steel, so for martensitic stainless steels with a high chromium content, which is above 9 weight percent, that we have more chromat present as chromats, so chromium oxides, compared to the cryogenic treated, where we have, of course, some nitrogen layers with the nitrates present, but also we have higher presence of iron oxides. So this is again confirming that we have specific layering compared to the conventional one, and this is happening that we have an improvement. With my test, with also the test with the tooling steel, we actually observed the improvement by 300% in a given environment by cryogenic treatment. So I think from this is already, that's why I said let's dive more into the fusion reactor, so for the energy sector and maybe in biomaterials, because there's a great potential in that. However, we have to be careful because, as I mentioned, at the same time we have a surface and bulk treatment. So in some cases, after application of cryogenic treatment, we don't need any more surface treatment, such as carbon nitrating or nitrating. However, in some cases, maybe we don't need any more coatings, but however, it's really based on application. For biomedical, we still say, please have coating because you don't know how it's going to react. So that's why you don't want some small pieces going to the bloodstream and so on. Anything can happen.
Yeah, for sure. So it seems like you have proven it improves many qualities and properties of the materials, not only at the surface, but as a bulk, it depending on the material, of course. However, I was thinking, is this thought on, like, can you treat the piece when it is final, or is the material that we are going to use to make something? So for example, before mash, like I was thinking, well, if we weld that, then we screw the treatment, just like with any post-weld heat treatment, it's like, we have to be careful with that. So what is the application that you can see is the final product or the material to complete the component?
Thank you for a very good question. So it can be material, component, or actually the final tool. So from Canada, Deep Cryogenic International's company is actually they have the biggest chamber for that in the world, the whole machines which are used for the mining industry.
Wow.
So that the treatment can be really different. However, there's also depends how our treatment bulk is going to be very, so thicker we have the bulk, of course, the treatment will not go so much in the deep. So we have to maybe several steps and so on to do how deep can penetrate the treatment. So this we have to be careful with that. But for the surface, what I need in the mining industry, it's for perfect.
Of course, because it's only superficial. Yes. So many, I don't know, microns or millimeters depth. and that's it. But we can adjust that,
Yeah.
so it will. So where else do you see these? Like you've mentioned biomaterials, you mentioned mining, you mentioned energy, that's nuclear now. Where else can this be used?
So actually, the first research is an interesting fact. Is actually was done by NASA, because when the first shuttle came back from the vacuum cold space, outer space, back to the Earth, they observed on aluminum alloy actually, oh wow, it's more tough and has a higher hardness. So what is going on? So actually, first it did like, oh okay, could be something practical. However, there are also companies how they're providing is more like a try and error principle. So you just throw it something in and you say, oh okay, it's not working. So without any basic knowledge. And for example, in the United States, there were also companies where they use cryogenic treatment to remove stains from the clothes. So you see, applicability is quite a variety, and also why you can use it and so on. So I would say, as I said, from also, for example, I also observed that it can also not be only used on ferrous alloys or not ferrous. It can also be used in ceramics, polymers, what I observed, and also composites. So quite a variety of them. Again, the treatment, cryogenic treatment, is really dependent on which material you're going to apply. Just like, give me an example. On steel, let's say we usually 24 hours exposure, whereas in titanium, so non-ferrous alloys, 48 hours exposure. So this is the most optimal one. But you will see also treatments, even after applications, after a week, they said that there's still changes happening and it's the best procedure. But here we have to also think about costs. So this, I would say, cryogenic treatment is cost effective. Why? Because also we can cut in costs, because if we prolong the life cycle, which we asked me before, so calculations showed, and also what the testing showed, is we can prolong life cycle by 3.5. So that's a lot, 3.5 times. That means we also have a lower maintenance costs. And also if you don't need additional treatments afterwards, that means, cool, we also optimize with that. So we really can talk about cutting operating costs. And at the same time, because when I'm using liquid nitrogen, we don't have any additional CO2 emissions in the environment. So we can also talk from this perspective, it's a green technique.
Oh, wow, that's amazing. And how much is the initial cost? We normally get, when we get into cost, it's a slippery soil, right? It's like, you're going to save that much. Yeah, but how much is going to cost me now? So it has to be thought as an investment that you will, like you're saying, sustainable operation, less maintenance, and then prolonging the life cycle. So obviously there is a safe like cost within the long term. What about the short term? Is that like compared to I don't know, TSA, thermal spray aluminum, or any other coating? Obviously those are only applicable to some things and are only superficial, not the whole material.
Yeah.
So I cannot think of anything that is only one thing that I can compare it with, because if you do post-well heat treatment, you can go to the deep, but then you need your superficial, like thinking on corrosion here, still need the superficial barrier. So, but with this one will be that, like equating, that is what I can quickly think about that. And by the way, this has not been a script for everyone that is watching us. We are going, with this. And Patricia, you're doing an amazing job at following with all my questions. So how is that comparing, like the initial cost?
So initial cost, I cannot say the numbers, because it depends what you decide, which type of treatment, which media, and so on. I would say it's cheaper, because you don't need to use just on the materials, the raw material, but you can also do at the final components in a machine. You just put it for several hours. Oh, look, and it's done. So, how? Here I would say then you have a cooling system, a chamber, because for example, what I'm using, also what kind of cryogenic treatment you're using. You can have gradual immersion, nebulization, and there we go with the cross. So gradual immersion, just put this in a bucket and that's all, for several hours, and that's all. However, if you go to nebulization, which is more specific case, so you cool down the air, which is your components around with cryogenic, so with the coolers such as liquid nitrogen, and now we're going to go up the numbers. Then you have also method where you can do gradual immersion and nebulization together. These are the costs that are going up, but I would say it's cheaper than nitrating or carbonitrating. Because, for example, if you get already raw material that's already from the industry, that's already hardened, and if you know that afterwards you don't need any additional steps of tempering, it's cheaper. You just buy, you can buy liquid nitrogen, which is, of course, the cheapest of those three. Also, we have to be careful if we use, of course, liquid hydrogen. Again, be careful with that. Don't use it if not necessary.
Don't do this at home.
See, if you go the temperatures to -80, you can use the dry ice, and you just for several hours, okay, and so on. So usually also with the colleagues at the work, they're also like, oh, okay, I'm gonna improve my knife for the home, so they just use a dry ice or liquid nitrogen you can buy for several hours, and there you go, it's improvement already.
Wow, interesting. Okay. So definitely I can see lots of applications, and then with the beauty
Maybe automotive industry also. So we have Harley Davidson, which are components also exposed into cryogenic treatment in order to prevent corrosion wear to progress. And Yamaha is also for these brass and string instruments, for example.
Wow. So there are already proven applications that are currently commercial out there that people are using to improve. That is very interesting. And it is really nice to see how, and we see this a lot, like how all correlates. Like improving the material properties will improve your life cycle, which will give you more sustainability, which will reduce, in this case, emissions because you're not applying, any of those nasty coatings that have VOCs or any of that. So it's when we start really looking into that, it really has a lot of benefits for everyone that is involved. Even like maintenance folks don't have to do as much and then extends the longevity. So it's really interesting. Well, thank you for sharing all that. I was like coming back into the years when I was a student and I had those, charts of the cycling and then the microstructure, how it will shrink and all that. How you ended up doing this research? Because you said NASA, it was like, something improved here. So it was like a mistake. Good for humanity, I guess. How did you end up on that field?
Just before I answer you that, I would like to say we also have negative results in the studies. And why is this? Is really strongly which temperature you use, and as we just explained before, which factors do you use. So for the same steel, you can also get a negative. So there's so many unknown factors still to cryogenic treatment. We have more questions than answers, also about the mechanism. So that's why I'm also trying to do advanced synchrotron neutron center measurements in order to observe in situ what is happening and so on. So that's why I don't want to say everything is positive. Yes, we can also have a negative. For example, if you have a higher hardness, you're going to have a lower toughness. So it goes, hand by hand. Just that we know it, that we understand when we apply. So how I came to that. So my background is geochemistry. And I wanted to do something different in material science. Then I saw this cryogenics with my previous mentor. I was like, okay, let's try it. To him, I said, I have a different background. He said, no worries, you just have to learn. So I learned a lot of things in the first year of my PhD. I had to earn, it's like a short course of everything in 1 year to have to get of material science. I specialize, of course, on the seals analysis, which I have. But yeah, that's what I was interested in. That's also when we were talking, okay, you have a surface in a bulk. Okay, I did more in my PhD in a bulk. But now with my postdocs, I'm doing more on the surface, which I'm also now really interested. And this also brought me, so first law was isotopes, let's say, now to the second law is atomic force microscopy, which I'm also applying and trying different modes in order to really research what is going on in regards, for example, to piezoelectrical modes, to electrostatic, magnetic forces in situ in regard to cryogenic treated material.
Wow, it's very interesting. Like it's amazing to see someone saying, I was very interested into the atomic, form of matter. And then I was like, normally people will be like, yeah, I want to save lives or I want to, but meeting someone like you is very interesting. So thank you for sharing that. And being a field where it is like you're 0.02% approximately. Obviously, you are the minority of the minority, and we spoke about that in our previous episode with Charo and all that. But it shouldn't, there are not a lot of role models that you can follow in that field. Like you're pretty much like opening up. How is that feel for you?
it's quite challenging, and you have to not just challenges that they're given to you. You have to also challenge yourself. When I came to the field, of course, I was just shocked. There is nothing, no support also, and so on. But then you have to find the nice people that support you. They say, oh, look, let's do that. I said, look, I have an idea. Can we just do something? Oh, I said, let's just try this technique. Oh, look, it actually worked. And so on. So you see, you have to try. You have to be curious. You have to explore. And you shouldn't limit yourself. But yeah, there are quite the challenging things that can happen, but it shouldn't take a will away, Yes, you have to be the will and also the change you want to see. So that's why I said, I'm going to stick to that. I'm going to do that. And I'm also going to advocate for women in SM, women minorities, of course, in that. But yeah, but also, it's challenging. I was at the last conference, the Society of Women Engineers in Munich this year. And when I gave a talk on the given topic, there was a woman that approached me and said, I'm so inspired to see that even women from Balkans, so I'm a Slavic person, so Slavic nations, let's say, can actually achieve and give something like that. You're really a role model. So afterwards, I talked with her. I was just like, oh, wow, I have now even bigger responsibility now. That's true. I come from the region called Slovenia, so country, which is a mixture of different nations, that because of the history. And I would say when she said, yeah, even from Balkan, you can see, wow, you're true inspiration. I was like, thank you so much. And now I have a bigger responsibility now. I cannot disappoint that woman. And that's how it goes,
Yeah, I heard the other day something that I don't even remember where I heard it, but it was like, you're not doing this for yourself, but for all the other girls that come, for example, from your countries, from Slovenian countries, or that look like you, or that speak like you, or that have that one thing that you have. So I agree, it's a huge responsibility, but we are doing it together, so it's better, and then we feel more, less alone, and then we can do, like, we are doing a lot of things together, and that is in its own a huge thing. So thank you for opening up the path for other girls in cryogenics that love the atoms. And then if there is any girl there like wanting, like feeling weird because the atoms call you, don't feel weird. Here we have Patricia, and she loves atoms and matter, and look where she is now. So you mentioned that you're going into the Marie Curie now. Congratulations.
Thank you so
And
much.
what does that mean?
That's me now. It's a really great achievement, of course. And it means more responsibility. And also, I want to take my advocacy for the women and minorities to the next level. So actually that we there, I hope that some changes will be more now. And also that we attract people to see that, no, not everything what is happening is right, and it shouldn't be that way. We have to change that. So also, for example, I'm also equality and diversity postdoc representative from Home MPG, from Home Max Planck Society. And I was also approached this summer by LGBT community when say, oh, also this is happening. I was just like, oh, wow. Oh, okay. So let's change it. So please now for the next, for example, semester, I'm saying it's better that one of you is selected to be representative, because things have to be changed. Because then you see with different eyes and what is not there. For example, I was also surprised with disability. For example, my colleagues who are disabled here, there's no promotion on what can help and so on. So we have to change that. So we have to see some things through the eyes of different people, and that's very important. I see from my perspective, but if we change some people, maybe I hope we get some small change. That would be great.
And there might not be changes all across, but you might change the way someone approaches someone. And that is huge on its own. Like the amount of people that have come to me and say, I watch or I listen to that podcast, and you know what? I never in my life I imagined that could have been still happening, or I've never imagined this is something that happens. And now I am super more conscious about it. And the amount of people that come after we release a podcast and they are like, oh, I have so and so to introduce you to, and they will be a good guest for the show and all that. I'm like, oh, wow, this is the ripple effect that we are looking for. So, and you have done so much, so, and with very little support at the beginning, so you have had to open up the path, and then for that I thank you, really.
Thank you for your support. You're always there to support me.
It's my pleasure. All right, we are at almost the end of our time together. Any last message for the audience? What will you like to say to the material business community?
So I would say, if you come to environment, they say or discriminate you or don't take you seriously because of your, let's say, disability or not adapt to be adaptive in this environment, I would say this is not your disability. This is your ability to see things different, and you will make a change.
Amazing. Really great closure. So thank you very much, Patricia, for coming once again. I wish you the best with this next chapter. Where can people find you said you had a paper published? Maybe you
So,
can send it to me and we can put it in the link in the podcast so people can read the research. And
thank you
then
for
if
having me, Monica. Of course, yeah, they can always check and get in contact with me via LinkedIn, but I also have on the website everything. So don't worry, I'm going to send to you.
awesome. Fantastic.
Thank you so much.
Well, thank you to all the material business community and to everyone that keeps sharing and, talking about us and sending our podcast to friends. This is how we grow. And then this is what motivates us to bring amazing people like Patricia and to learn about things that probably we would have not learned if we would have not talking to her. Thank you to all of you, and then keep posted for the next episode of Material Business. Thank you, Patricia.
The same.